Hmm. So very good morning, all of you. So in the last class, I have explained about the modes of the waveguides there. Okay, what if you take the TE mode, it is a transversive electric. If you take the TM mode, it is transverse magnetic. If you take the TEM mode, it is transverse electric and magnetic. And if you take the one more, it is what? It's an hybrid mode. Okay, so in the transverse electric, so what that electric field it is going to be, it is perpendicular, it is along the opposite walls there. Okay, and if you take the TM, okay, what if you take the magnetic field, okay, it is parallel or and I'm sorry, it is to the perpendicular to the this side walls. Okay, and along the direction of the propagation, it's not having the magnetic field. In the same way, in the transversive, there is electric, so that what that electric field is not along the direction of the propagation there. Okay, if you take the it is TEM mode, so it is both the E fields and the H fields are going to be perpendicular to each other there. Okay, so so it was explained in the previous class, and also its field representation is also being studied. Okay, and in this class we are going to study about the microwave semiconductor devices here. Okay, this is the class 5 of the unit 1, which is concerned to the advanced communication. It's for 5th semester, okay, diploma EC. Okay, and so in this class we are going to study about the introduction to the microwave semiconductor devices, and we'll see only the types. It is which is concerned to the syllabus. It is for the microwave semiconductor devices types, and also we'll see the impact diode, its constructions, working, and efficiency, advantages, disadvantages, and applications of the impact diode. So all this we'll see in this class here. Okay, so initially if you take the introduction to the microwave, it is semiconductor devices. So it is what this it's microwave semiconductor devices. Already you know the definition of the microwaves. Okay, if the signal is to be represented in the range of it is 3 gigahertz to 300 gigahertz, or it is 300 megahertz to up to 300 gigahertz. So it is called as the microwave signal. If you take the microwave semiconductor devices, means it can able to operate with the microwave signal. Okay, it is itself is called as of the microwave semiconductor devices. And in this case, what is microwave semiconductor devices are also called as an avalanche transit time devices, because it is going to be get operated with the negative resistance here. Okay, so it is also called as the avalanche transit time devices. So if you take the microwave semiconductor devices, the another name is the avalanche transit time devices. So in this case, what happens? It is the process of okay, having a delay between the voltage and the current in avalanche together with the transit time. This through the material is said to be the negative resistance, and the devices, okay, that helps to make a diode exhibit this property. So this property means it is a negative resistance property, are called as avalanche transit time devices or the microwave semiconductor devices. Okay, suppose consider that if there is a delay between the voltage and the current, and what that delay is to be measured in terms of the transients. So in avalanche together with the transient time, so that we can able to concentrate this word here. Okay, if there is a delay between the voltage and the current in avalanche together with the, it is a transient time, so that how much phase it is going to okay change in order to reach from the one end of the diode to the other end of the diode. It is explained afterwards with the block diagram, or it is with the circuit diagram. Okay, so it is itself is called as of the transient time here, and it is to be represented, or it is to be based on the negative resistance of that material here. Okay, and if you take the devices that helps to make a diode to exhibit this property of the negative resistance itself is called as an avalanche transit time devices or the microwave semiconductor devices. Understood the definition? So if you take the microwave semiconductor devices are those it is which exhibit the property of the negative resistance are called as the microwave semiconductor devices. Okay, and if you take the types of the if you take the types of the microwave semiconductor devices, if you take the semiconductor devices means it is what the hundreds of the semiconductor devices are available. And if you take the microwave semiconductor devices also, it's having it is more number of the semiconductor devices. It is micro semiconductor devices. And as per the syllabus, so has been considered for the diploma. It is represented only with the two examples here. It is one is an IMPATT diode, another one is the TRAPATT diode. Okay, so it is these two are called as the main it is microwave semiconductor devices here. Okay, so if you see the IMPATT diode, it is why it is called as an impact here. So the full form of the impact is it is impact ionization avalanche transit time diode. Already you know that it is what the meaning of the avalanche transit time. Avalanche transit time is an indication of the microwave semiconductor device. Okay, so I in the impact IMP, it is indicating as an impact ionization, and A indicating the avalanche, and what is the TT indicating the transit time. So the full form of the impact is impact ionization avalanche transit time diode. Okay, and it is the microwave, okay, semiconductor, okay, diode. It is nothing but the diode here. What the device here is, it is in the form of the diode here. Okay, so the impact diode is an RF semiconductor. RF means it is a radio frequency. RF semiconductor device, okay, that is used for generating the microwave, okay, radio frequency signal. So the actual meaning of the avalanche transit time, it's nothing but the material is consisting of the negative resistance, and it is used in order to make use of the microwave signal. So the impact diode is an it is a radio frequency semiconductor device. It is used for generating the microwave, okay, radio frequency signal. Understood? It is in the form of the microwave, and it is a high power semiconductor diode, and it is used in the what high frequency is microwave applications. It is with the ability to operate at a frequency between about it is 3 to 100 gigahertz or even the more. Okay, its operating frequency capability is from 3 to 100 gigahertz or above the 100 gigahertz also it can able to get operate, and it is relatively of the what high power capability. The impact diode is having the high power capability. Understood? So I am going to repeat it in brief. So the full form of the impact is impact ionization avalanche transit time diode, and the impact diode is an RF semiconductor diode. It is of the radio frequency device, and it is used for generating the microwave radio frequency signal, and it is of the high power semiconductor diode. It is used in the what high frequency microwave application. So high frequency means how much? It is from it is 3 to 100 gigahertz or above the 100 gigahertz also, and it is relatively of the what high power capability. This is about the semiconductor diode. Okay, and if you take the construction of the impact diode, so it is constructed. So it is constructed. It is with the P plus N and the N plus, or it is what N plus. It is P or and P plus combination. So in this diagram, it is constructed with the P plus, okay, N plus, so that you can able to see this is the diode here, and it is one terminal is called as the anode, and other terminal is called as the cathode here, and it is constructed with the P plus material, so that you can able to see this is the P plus material, and its width is approximately 2 micrometer, and it is to be followed by the N region, okay, and its width is approximately 3 micrometer, and it is to be followed by the what, N plus region. It is also called as the drift region, and it is approximately, it is a 10 micrometer, okay, and it is to be arranged as in this way, okay, and after that it is to be operated under the avalanche means it is to be connected under the reverse bias here. So it is for the anode, it is to be connected with the negative terminal, and for the cathode it is connected with the positive terminal, and the voltage applied is very high. It is approximately, it is 400 kilovolts per centimeter has been applied. It is a high potential gradient is applied to the back bias, the diode. What this back bias means, under the reverse bias, and it is hence the minority carriers is going to flow across the junction. And in this case, I said that it is having the variation in the voltage and the current. So how much amount of the time it is going to take in order to travel the electrons or the holes into the drift region in order to reach the cathode terminal. So it is itself is called as the transit time, okay. So if again I am going to repeat the construction of the IMPATT diode. It is constructed either with the P plus N and the N plus, okay, it is P plus N and the N plus, or it is N plus P and P plus combination, okay. And if you take the P plus, it is approximate width is equal to 2 micrometer. It is to be followed by the N region approximately 3 micrometer. It is to be followed by the what, N plus drift region. It is approximately, it is 10 micrometer, and it is one end, it is at the P end is called as the anode, and what this N plus drift region end is called as the cathode, and arrangement is to be under the back bias, so it is under the reverse bias. So this anode is to be connected to the negative terminal, and what is cathode, it is to be connected to the positive terminal, and it is approximately the input applied is equal to, it is 400 kilovolts per centimeter. Understood? It is the working of the an impact diode. I'm sorry, it is the construction of the impact diode. And if you see the working, if you see the working of the impact diode, in this case you can see an application of the RF AC voltage. It is of the radio frequency AC voltage if it is superimposed on the what, high DC voltage. So the increased velocity of the holes and the electrons results in the additional holes and the electrons. It is by thrashing them out of the crystal structure by the impact ionization. That means that already the it is very high DC voltage has been applied. You can see this is the very high DC voltage, which is approximately, it is 400 kilovolts, and and with this, if you apply the RF, it is the radio frequency AC voltage, and it is to be get superimposed with the DC voltage. So the RF AC voltage is to be get overlapped with the, it is what, DC voltage. And if this is going to happen means the increase in the velocity of the holes and the electron takes place, and it is going to generate again the extra, that is an additional holes and the electrons, in which it is going to be drift with the impact ionization. How means, if the original DC field applied was at the threshold of it is developing this situation, it is then it leads to the avalanche current multiplication, and it is going to be continued. And it is due to this effect, the current pulse, it takes a phase shift of the 90-degree. If it is to be compared with the voltage signal, so the current pulse, it takes a phase shift of the 90-degree. However, instead of it is being there, it moves towards the cathode. It is due to the reverse bias applied. I said that it is going to move towards the cathode here. So how much amount of the time takes place in order to travel into the drift region, it is going to be decided by the phase here. It is due to this effect, the current pulse, it takes a phase shift of the 90-degree. Instead of being there, it moves towards the cathode. It is due to the reverse bias applied. So, how much amount of the time taken for the pulse to reach the cathode, it depends upon the thickness of the N plus layer, and which is adjusted to make it 90-degree phase shift. So, it is what I said, how much amount of the time it takes for the electron or the holes in order to travel the entire way of the n plus drift region, it is going to decide the phase shift, and its width is to be adjusted in such a way that it should undergo the phase shift of the 90-degree. So you can able to see it's 10 micro, it is meter. Okay, so it is the time taken for the pulse is to reach the cathode. So it depends upon the thickness of the N plus layer. This is the drift layer, which is adjusted to make it the 90-degree phase shift here. And it is now a dynamic radio frequency. Okay, negative resistance is proved to exist. It is itself is the requirement of the microwave semiconductor diode. Okay, if it is having the negative resistance, okay, so that it can able to get operated with the microwave signal. So for that purpose, it is having the radio frequency. It is what the negative resistance is going to be existing. It is based on this operation. It is so the impact diodes, it acts as an oscillator as well as an amplifier. Understood? So again I am going to explain the working of the impact diode. So initially, so the RF AC voltage signal is applied, and it is to be get the superimposed on the DC voltage. And after superimposing, so there is an increase in the velocity of the holes and the electrons, and increasing in the electricity, increasing in the what velocity means the speed of the holes and the electrons, it is going to generate the additional holes and the electrons. Okay, it is itself is called as an impact ionization. And if the original DC applied to the threshold of developing, it is this situation, so the avalanche current multiplication takes place, so that electrons and the holes is to be get multiplied, and it is going to be continued. And in this case, if you take the current pulse, it takes a phase shift of the 90-degree. Instead of being there, it moves towards the cathode under the reverse bias applied. And if you take the time taken for the pulse to reach the cathode, it depends upon the thickness of the N plus layer, and so that it is to be adjusted such that it should have the phase shift of the 90-degree. Under this phase shift, it is itself is called as the dynamic RF negative resistance. And in this way, the impact diode is acting as an oscillator as well as an amplifier. Okay, understood? This is the impact diode. It is construction, and this is the working of the impact diode. So this is very, very important. And if you take the equation for the efficiency, The efficiency of the impact diode is to be represented by eta is equal to, it is PAC divided by, it is PDC. PAC is an AC power, and if you take the PDC is the DC power. And it can also be represented, I think you know the, the formula for the power. It is P is equal to, it is V into I. Okay, so if it has to be placed in this equation, PAC is equal to VA into IA, in A indicating an AC. In the same way, if you take the PDC indicating the VD into ID, or the D indicating the DC here. So this VA and IA is an AC voltage and an AC current, and what this VD and ID is the DC voltage and the DC current here. It is the equation for the efficiency of the impact diode. And after that, if you take the advantages of the impact diode, it is its operating range is higher, so that it is going to be operate from, it is 3 gigahertz to up to 100 gigahertz frequency, or the more also. So its operating range is higher here. Okay, and here in this case, it produces the what, the higher discontinuous wave power output, it is per unit. So if the RF signal is to be get overlapped with the DC signal, it is going to provide the continuous, power output here. If you take the disadvantages of the impact diode, it is noisy, as the avalanche is the noisy process. So if after the superimposing of the AC and the DC, so it is going to undergo the impact ionization. So it is going to do the multiplication of the electrons and the holes there. And in the under this one, it is going to be what happens. It is going to exist the noisy. Okay, and if you take the tuning range is not good as in the gun diodes. In the gun diodes, it is so it has been assumed as, or it is having the exact tuning setup. But in this case, it's difficult to set up the tuning here. And it is to run an impact diode, a relatively what high voltage is to be required. Obviously, I said that the input you are applying is approximately, it is 400 kilovolts. It's not volt. Okay, 400 kilovolts is to be applied here. So it is relatively in need of the high voltage here. All these are the advantages and the disadvantages of the impact diode. And after that, if you take the applications of the impact diode, it is used in the n number of the applications. It is used in the microwave oscillator, used in the microwave generators, used in the modulated output oscillator, used as the receiver of the local oscillator, used as the negative resistance amplifications, used in the intrusion alarm networks, used in the police radar, used in the low power microwave transmitter, so the FM telecom transmitter, the continuous wave Doppler radar. Okay, all of this you see in the next chapter. Okay, all these are the applications of the what impact diode. Okay, so in this class we have been studied, it is what's the definition of the microwave semiconductor device. It's nothing but what, it's nothing but an avalanche transit time device. It is having the negative resistance, that itself is called as an avalanche transit time of the microwave semiconductor device. And it is to be classified into the main two types. One is an impact diode, and other one is the trapper diode. And if you take the impact diode, its full form is impact ionization avalanche transit time. Okay, it is going to make use of the RF frequency signal. It is a radio frequency signal. Okay, and it is to be operated under the what high power. Its operating frequency range is from, it is 3 to 100 gigahertz or even the more here. And its construction, it is to be constructed with the P plus n plus, or with the n plus P or the P plus combination. And if you take the P plus combination width is approximately, it's 2 micrometer, the what this n is approximately 3 micrometer, what this is n plus represent approximately, it is 10 micrometer. And it is one end is called as an anode, and the opposite end is called as the cathode, and it is to be arranged under the reverse bias. if you take its working, so this what the DC voltage is to be get overlapped with the RF AC signal, and it is going to increase the velocity of the holes and electron, and it is going to generate the additional holes and electrons, and it is to be get multiplied, and it is going to be continued. And what this current pulse, it takes a phase shift of the 90-degree, and it is going to be traveled, it is towards the cathode under the reverse pass. And it is what this thickness of the n plus layer, it is going to decide the phase shift. Okay, and it is going to generate the dynamic RF negative. Okay, it is what resistance. And if you take the efficiency formula, eta is equal to PAC divided by PDC. Okay, and advantages, operating range is high. It is going to produce a what the higher continuous wave power output. If you take the disadvantages, it is of the noisy. Its tuning range is not good, and it's in need of the high power. And if you take the application, it is used as an oscillator generator. Okay, modulated output in the local oscillator as the negative resistance amplification, intrusion alarm. It is police radar, it is low power microwave transmitter, FM telecom, and the continuous doubler, etc., etc. It is used in the number of the applications. If you take the sample descriptive questions of this one is, he may ask you to define the microwave semiconductor device, and he may ask you to list few microwave semiconductor device. He may ask you to define the impact diode. He may ask you to explain the construction and working of the impact diode. He may ask you to list out the advantages and disadvantages of an impact diode, or he may ask you to list the applications of the impact diode. All these are the possible questions. And in this case, the explain the construction and working of the impact diode is going to be the important one. Okay, it is going to be asked, it is maximum. Okay, and this is all about the microwave semiconductor diodes, especially the impact diode. In the next class, okay, so that we are going to study about the trapped diodes. Okay, yes, I am going to end up the class. Okay, thank you very much.